In this chapter of the course, we talk about varieties, some new kind of geometric objects. But before going to their definition, I want to look back a bit and give some motivation for why we need a new definition. So we have already introduced a nice class of ring spaces, which are the affine varieties. However, these have some limitations. So for example, an open subset of an affine variety is not necessarily itself affine variety. That was in the last video, A2 minus the origin inside A2 is not an affine variety. And then maybe a bit in the opposite direction, kind of affine varieties tend to be non-compact if we look at them, for example, in the complex topology. So we sometimes return to this setting of K, the complex numbers, and then we can see any affine variety as a subset of C to the n, and it has a topology given by the usual complex topology. And the claim here is that the complex topology on affine variety X is only compact if X is finite. And as an example, we can look inside A2 over the complex numbers. We can write down the vanishing set of some equation f, where f is the degree d equation in x and y, which is chosen kind of generically. So somehow basically you choose random numbers for these coefficients. And if you do that, the resulting topological space X with the complex topology actually looks as follows. It looks basically like a real surface, which looks like the surface of a donut with this number of holes, wherever this number comes from. And the kind of important thing is that it's almost the surface of the donut, except that, well, there's some points missing. So in fact, there's exactly d points missing in the sense that if you follow this solution set inside C2, then you see there will be some solutions which go to infinity. And basically they go to infinity along these kind of d small cylinders going away. And so overall as a topological space, it looks like the surface of the donut where you removed d of the points. So it is not compact because, well, you can have sequences going to infinity which don't have a limit in this space. And generally speaking, it's nice if you can work with compact spaces. And it's kind of frustrating that we cannot, apart from finite sets, we cannot get a single compact affine variety. What we would like to do is we would like to fill in these d missing points. So we would like to be able to get some varieties where the complex topology would give us such a picture. So like just this real donut surface with these points filled in. And how we can get this is we can look at spaces which are just locally like affine varieties. So they have a cover by affine varieties. And then these kind of previously missing points, these would be covered by a second patch, a second affine variety. And then we could get these nice spaces. So if this was a bit too hand-wavy and I said complex topology and so on, don't worry so much. It's basically just for motivation. But maybe another analogy, if you have seen manifolds before, then you have seen manifolds are, by definition, some topological spaces which locally look like open subsets of Rn. This is the definition of a topological manifold with some conditions which I omitted. And similarly, our varieties will be ring spaces which have a cover by affine varieties. So that's the definition essentially. And we write this down, and there will be a slight twist later. So for now, these objects which I described will be called prevarieties. So pre-variety is a ring space X which has a finite open cover by finitely many open sets, which are themselves as ring spaces isomorphic to affine varieties. And then morphisms of such prevarieties will simply be morphisms of the underlying ring spaces. So here you see it was kind of very economical that we discussed morphisms of ring spaces in general, because then we can not only apply them to affine varieties, but the same definition also gives us morphisms of these prevarieties. And notation-wise, when you have u inside X open, we still call the elements of OX of u regular functions. So if you take this sheaf of rings on X and evaluate it on an open set U, we just call the elements of this ring regular functions. And some remarks about the definition. So this open cover that appears in the definition, this is not part of the data of the prevariety. It's just enough that it exists. So we don't have to remember it separately. And then an affine, an open subset of a prevariety, which is an affine variety, this will be called an affine open set. So the condition here is that there exists a cover by affine open set. And then some examples. So certainly any affine variety is a prevariety because it's covered by itself. So that's easy. And then this set U, A2 minus the origin inside A2, this turns out to be a prevariety because it is covered by D of X1 and D of X2, which themselves are these distinguished open sets we have seen are affine varieties. And so this is a cover, as we like it, but it is not itself affine. So you really at least need two of these sets. More generally, any open subset U of an affine variety is a prevariety because it has a finite cover by distinguished open sets, and they are affine varieties. And this here followed because we saw that these distinguished open sets form a basis of the topology. And so before we had this complaint, one of the motivations which I started the video with was that affine varieties are not closed under taking open subsets. And here a short exercise is that at least this complaint is now solved with the new definition, because you can show that any open subset of a prevariety is a prevariety. So at least we have now arrived at a definition which is closed under taking open subsets.